Hello everyone, and welcome to the second part of Module 1, Unit 1, Rectilinear Motion. In this video, we're going to take a look at the three equations of motion, and this is specifically for rectilinear motion with uniform acceleration. Here are the three equations. We have S is equal to V naught t plus 1/2 at squared. V is equal to V naught plus AT, and V squared is equal to V squared, and that should be not a 0 for a subscript, plus 2AS, where again S is your displacement, V and V naught are your velocities, so you have an initial velocity, that's V naught, V0, V sub 0, and V, which would be your final velocity. We have a constant acceleration, and T for time. And you can see we are using the base units of either meters or feet, all with seconds. Some important notes about these equations. First, the acceleration must be constant. Constant velocity is a special case where acceleration is 0. Remember, I did say that the velocity magnitude is either 0 or it's constant, then the acceleration is 0, and always 0 unless there's a change in direction. So unless it's specified that there's a change in direction, then the acceleration must be 0. A free-falling body has an acceleration of 9.81 meters per second squared for SI units, or 32.2 feet per second squared, and that would be US customary units. Acceleration may be in any direction, so we need to specify the positive direction when we are completing our problems. A particle or object that slows down in the positive direction has a negative acceleration. So it is possible that we have velocity in one direction and acceleration in the opposite direction. We'll be jumping right in and solving problems by applying these three equations of motion. However, there are a number of points that I want you to consider when you are solving these problems. First and foremost, you need to read the problem carefully. It's good to identify all of the relevant information and also to identify information that really is not going to help us in this problem. Sometimes you are given extra information that is not of any use. So it's important to really understand what the question is asking. Next, I would like you to tabulate all the data. We can start this by first drawing a figure or a free body diagram, and then writing out all of the knowns. Within that, I'm also asking you to convert units. You should do that right off the bat. So as we saw in a previous problem where we had miles per hour, we converted those miles per hour to feet per second. Rather than trying to do that within an equation, we did it before even subbing into that equation. Next, you want to establish a coordinate system. As I mentioned, you want to, since acceleration can be either positive or negative, then you need to specify which direction is positive. Also within here, I would like you to write out the equations required. So sort of a step in between 3 and 4 here after you've established that coordinate system. It can often be helpful just to write out all three equations. That way there you can look and see which variables you have and which ones you need to find. Number 4, show all units and carry them through. It's easy when you're trying to solve these problems to just quickly write down the numbers, but just as easy as it is to write out the numbers without units, it's also easy to forget the units in your final answer, which will result in an answer being marked as incorrect on assignments and tests. So please make sure you show your units all the way through the problem. Last but not least, Number 5, study the answer and ask the question, does this make sense? It's one of the most important aspects of solving these problems is understanding whether or not the result you're getting is of consequence, if it matters, if it makes sense. Okay, so before we move on to motion of a projectile, Let's try one of the problems from the textbook. We're going to take a look at problem 1025. Okay, in this problem, it says that there's an object with negligible air resistance and it's dropped from a height of 60 meters. We want to determine how long it takes to land and the velocity at which it lands. So again, just going back here, we read the problem. Okay, we see that there's information. We know that it's a ball and it's at a height of 60 meters. It's going to go that full distance. We don't know how long it takes and the velocity at which it lands. So let's draw that out. We have a ball, and that ball is going to be dropped a full distance of 60 meters. It clearly has an initial velocity and initial time where V0 is 0, starting from rest right at the top, and that's at a time of 0. Throughout its fall, we know that there is an acceleration due to gravity, and since we're dealing with SI units, that's 9.81 meters per second squared. Okay, and what we want to know is what is the final time. So T1, we're not sure, and what's V1 at impact, just before impact. I'm going to establish a coordinate system, and I've written out all of the data and provided units, and they're all within base units. So I'm going to assume that to the right and downwards is my positive direction. And I want to write out the equations. Okay, first of all, for velocity, I know that velocity is delta S over delta T. I also know through the three equations of motion that S is equal to V0 T plus 1/2 AT squared. And V is equal to V0 plus AT. And V squared is equal to V0 squared plus 2AS. These are the three equations of rectilinear motion. Okay, taking a look at these three, we have a value for, go through here, we have a value for S, we have a value for A, the acceleration, that's the same thing, acceleration due to gravity. I also have an initial velocity, which is 0. So right off the bat, we can see right with this equation, we should be able to use that in order to solve for our final velocity. So let's go ahead and do that. So V is equal to, or V squared is equal to V0 squared plus 2AS. As I said, V0 is 0. So that means that V is equal to, I would have to take the square root of 2AS, so that's 2 times 9.81 meters per second squared times S, the displacement, which is 60 meters. So the velocity is equal to 34.3 meters per second, and it's clearly downwards, so we don't need an angle. We also want to find time. So let's go to the next equation. Next equation up, we have a final velocity, which we've now solved for. We have an initial velocity, and we have acceleration, so we can use that one to determine time. So V is equal to V0 plus AT, where again V0 is 0. So if I sub in 34.3 meters per second is equal to 9.81 meters per second squared. We're going to multiply that by time. If you take a look closely at this, you'll actually see that the units work out. If I have meters per second, now I divide both sides by meters per second squared. And so I'm left with time. So T is equal to 3.5 seconds. And there is the solution for both velocity and for time. So as I mentioned, it is very helpful to write out your three equations and go through and see which ones we can solve for. Okay, next we can apply these three equations of motion to motion of a projectile. In the last problem, we just looked at a ball that's being dropped. Now imagine a ball being thrown. So with the ball being dropped, it is just moving in one direction. However, now that the ball is being thrown, it's moving in both the x and the y direction. So it does complicate things a little bit in that now we need to apply those three equations of motion in the x direction and the three equations of motion in the y direction. It's very important to remember you cannot mix and match x and y direction velocities as well as x and y direction displacements. Okay, that's why we need to keep them separate. However, time is the one variable that bridges the gap between these two sets of equations, and we're going to use that to our advantage when we're trying to solve for our terms in these problems. So in motion of a projectile, the free flight motion of a projectile is often studied in terms of its rectangular components, since the projectile's acceleration always acts in the vertical direction. All that's saying is that for any of the problems that we look at for projectiles, a x is going to be 0 and a y is going to be 9.81 meters per second squared, acting downwards. When air resistance is neglected, the only force acting on the projectile is its weight. And again, that is due to that acceleration right there. Therefore, the projectile has a constant downward acceleration equal to the acceleration of gravity. And there are examples 10.7 and 10.8 on page 348. Now, I find it quite helpful just to draw out an example before we get into the problems of motion of projectiles. So I mentioned, taking an example of a ball, and we are going to toss this ball. So it is going to follow a trajectory similar to a parabola. So we have our first point and we have our second point. In the x direction, we have a total displacement, and this would be our s sub x displacement in the x direction, and that takes place over the entire time of projectile motion. We also have an s sub y. Of course, the displacement in the y direction between the first point and the last point, so where it starts off to where it ends, if of course it ends in the same plane, its displacement is 0, right, in the y direction. However, it does have a maximum displacement at the top of that parabola, right at the top, and that is at half the time, exactly half the time here. Also of importance is the fact that there is an initial velocity, goes off at an angle. This would be v naught, and then we have a final velocity. Both have actual values, they're not 0 if you're taken just after launch and just before, so there is a v naught and a v1. And in both of those cases, they have components. So we have a v naught x and to the right, and going up here, we have a v naught y. Similarly, we have a downwards v1 y, and to the right, a v1 x. This is where we would have to break those up. We can't solve for velocity at an angle like this. We need to break it up to x and y components. Okay, similarly, at the top here, we have a vx and we have a vy, okay, but that vy here is 0, right at that peak. So some points here. The free flight motion of a projectile studies the rectangular components. Okay, so that's again just what we talked about here. So we're going to apply these using our three equations of motion in both directions. So let's start by taking a look at example 10.7. Okay, in this problem, it states that a projectile is fired at an angle of 20 degrees from the horizontal with a velocity of 100 feet per second. If it lands 2.12 seconds later in the same elevation, how far did it travel horizontally? So let's draw that out. We have a projectile with an initial velocity. We can say that that's v naught is equal to 100 feet per second. It travels a distance, which is what we're trying to find, and the total travel time is 2.12 seconds. The only other piece of information that's given is that the angle is 20 degrees for that initial velocity. And so what we're going to have to do is we have to remember that that initial velocity needs to be broken up into x and y components. So here is our v naught. V naught is equal to 100 feet per second. We know that it's going to have v naught x value, and it will have a v naught y value. Within there, we know that this is a right angle triangle, and since this is 20 degrees in this corner, we know this must be 70 degrees up in that corner there. So what we want to do is determine the components of velocity. We can start with v naught x, which is just equal to, using that triangle and trigonometry, say that that would be v naught cosine 20 degrees. Which is equal to 100 feet per second times cosine 20 degrees. Therefore, v naught x is equal to 94 feet per second to the right. Okay. And we can do the same thing for v naught y. Except instead of cosine, it's going to be sine 20 degrees. So that's equal to 34.2 feet per second upwards. And now it would be helpful to write out the equations, the three equations of motion. So S is equal to v naught t plus 1/2 at squared. V is equal to v naught plus at, and v squared is equal to v naught squared plus 2as. Now keep in mind, as I said before, we would have to write this out 6 times. 3 for x direction, 3 for y direction. But when you think about it, the only thing that's really given here is our x direction displacement. No, that's what we want to find, sorry, is the x direction displacement. And since we know the x direction velocity, the question is whether or not we can determine the value for s, so that x direction displacement, just based on what's given right now, or is there anything else that we can do? Well, one thing to keep in mind is that the acceleration in the x direction, the other thing we know is the x direction acceleration is 0. It's always 0. The only non-zero acceleration is in the y direction. So then that means that this term would go to 0, which doesn't really help us. That's just saying velocity equals velocity. But it helps us with this term because then what it's saying is that s is equal to v naught t. So if we were to write that out in terms of x components only, it would be sx plus v, sorry, not plus, but equals v naught x times t. So that means that sx is equal to 94 feet per second times our time, which is 2.12 seconds. So Sx is equal to 199 feet. Remember, it is a displacement, and so it still it is a vector, so it's to the right. And so our final answer here is that it displaced 199 feet to the right. Okay, next we'll look at example problem 10.8 from the textbook. So that's just on the next page. And here we have another projectile, and it's fired with an initial velocity of 200 meters per second inclined at an angle of 40 degrees. It lands at 100 meters lower than the initial point. So we want to determine the time of flight, which is irrespective of x or y. We want to determine the horizontal displacement, so that's the x direction displacement. And lastly, we wanted to determine the final velocity. Now, the final velocity, just like an initial velocity, has both x and y components. That means that we'll need to find the x and y components, both of them, for that final velocity. So let's start by drawing out the figure. Okay, so here are the three things we want to find. Here's our figure. We also know that the initial angle is 40 degrees. We also know that that final velocity would have two components, just as the initial velocity. Okay, so it's helpful to draw those in to remind ourselves. So v0x, v0y, as well as a v1y and a v1x. Okay. Also quite helpful once we're happy with the figure and we have everything written down to just write out those equations, three equations of motion. So we have S is equal to v0t plus 1 half at squared. V is equal to v0 plus at. And last we have v squared is equal to And last we have v squared is equal to v0 squared plus 2as. So our 1, 2, 3 equations of motion. So as I did before, I'm going to draw out that initial velocity. So that's v0 is equal to 250 meters per second. And it's helpful just to see those components. Right? So v0x and v0y at 40 degrees. And if that's 40 degrees, that means that the upper angle is 50 degrees. And so as we did before, we are going to figure out our components. So v0, okay, so v0x is equal to 250 meters per second cosine 40 degrees, which is equal to 192 meters per second to the right. And our v0y is equal to 250 meters per second sine 40 degrees, which is equal to 161 meters per second upwards. We also know that the displacement in the y is equal to negative 100 meters. I could make that positive. This is where it's really important to decide what's going to be positive, what's going to be negative. Because if I decide that downwards is negative, and I just wanted to show that in this example, then our acceleration or acceleration due to gravity, g, also has to be negative. You can't have one or the other. If downwards is negative, then that means anything, any displacement or velocity or acceleration in that direction must be negative. You have to be consistent or you will not get the right numbers. Okay, so sometimes, like this one, there are a couple of different ways of solving it, some more complicated than others. And so let's just start by doing it very similar to how they do it in the textbook here. This is the most straightforward method, believe it or not, for this particular type of problem. Since we do have a displacement and we do have an initial velocity, let's use, we go over here, let's use equation number 1. And again, we're going to use that in the y direction because we have a y displacement and a y acceleration. Sy is equal to V naught y t plus 1/2 ay, and that's t squared. So again, it's a negative direction for that displacement, so negative 100 meters times 161 meters per second. Now it's positive because its initial velocity in the y direction is upwards, times time plus 1/2 negative because it is downwards for acceleration, 9.81 meters per second squared, times t squared. So if I rearrange it here, you'll see I'll get something like this, 4.9 t squared minus 161 t minus 100. Remember back to the first video, this looks like something where we can use the quadratic formula to solve, and we're going to get two values. This, again, is solving for where that parabola would cross the horizontal axis. So we're going to get two values here. We'll write it out. T is equal to, remember it's negative b plus minus the square root of b squared minus 4ac all over 2a. And you're going to say, well, what are these a's, b, and c's? Remember, that's just from the quadratic formula, where our a value then is this, our b value is this, and our c value is this. So we can sub those in. So you should have something like this. T is equal to 161 plus minus the square root of that 161. It's a negative here. A negative and a negative gives us, in that first one, a positive. So then this one's a negative squared minus 4.9 times negative 100 all over 2 times 4.9. And so you should from here get two values for t. Okay, we will get t is equal to 33.4 seconds, or you're going to get t is equal to negative 0.61 seconds. So clearly that is where it passes the x direction where it passes that negative in the x direction. So at t equal 33.4 seconds and t equal negative 0.61 seconds, mathematically this works because that is where that parabola would cross the x axis, and it does that twice. But obviously, practically for this problem, the second one does not work because we can't go backwards in time. And so we are going to use t is equal to 33.4 seconds to continue our solution. So we did solve for the first problem all the way back here. We do have the time of flight, so that is 33.4 seconds. Next, we want to find the horizontal displacements. Okay, we know that the vertical displacement was 100 meters downwards. So what is the horizontal displacement? So we're going to solve for b now. And remember, it's helpful to write this out to include your whether you're doing it for the x direction or y direction. So I'm doing it now for the x direction. So v naught x, if you remember, is 192 meters per second to the right. Therefore, if we use, say, this equation, s is equal to v naught, so sx is equal to v naught x times t plus 1/2 ax t squared. This whole second term goes away because x direction acceleration is always 0 in these problems. So sx is equal to 192 meters per second times time, which we just calculated, 33.4 seconds. So our x direction displacement is 6,400 meters. There is our displacement. Okay, last problem now. We need to solve for the final velocities. We want the final velocity at landing. Now, for this one, we are going to start with v is equal to v naught plus AT, and this is for the y direction. Okay, so it's helpful to write it out as Vy is equal to Vy naught plus AYT. So Vy is equal to V naught y, which is 161 meters per second. It's going up, so that's okay, minus the 9.81 meters per second squared times our time, which is 33.4 seconds. So V naught y is equal to negative 167 meters per second. Okay, so we solved for the velocity in the y. Now you'd think you'd have to do the same thing for the velocity in the x. But let's think about this for a second. We had a change in velocity from the initial velocity to the final velocity in the y direction because we have an acceleration, and that's the acceleration due to gravity. But we've been saying from the beginning that there is no acceleration in the x direction. The only acceleration is that acceleration due to gravity. So that means whatever initial velocity you have, the final velocity will be the same because there is no acceleration in the x direction. So we can state that since we have a velocity in the y direction of negative 167 meters per second, we also have an x component of 192 meters per second. And since these form the basis for a triangle, if we go all the way back, here is the triangle right here. Okay, so we have an x, we have a y, so in order to figure out the final velocity, we just need to use the Pythagorean theorem because it is a right angle triangle. Therefore, the final velocity is equal to, would be negative 167 squared plus 192 squared is equal to 254.5 meters per second. But hold on, that's not the final answer. Why? Because we need to find its value relative to horizontal. So we need a direction. So we can do that since we know it's a right angle triangle. Tan theta is equal to 167 over 192. So therefore, theta is equal to 41 degrees. So VF is equal to 254.5 meters per second at an angle of 41 degrees.